In this video, we'll look at simplifying radical expressions. Remember that a radical expression has the index, which we call n, and a radicand, which is the expression that's underneath the radical. Here we'll look specifically at radical expressions where the radicand is not a perfect root of whatever index it is. So not a perfect square or perfect cube or perfect fourth, etc. Let's start with a square root. Something like the square root of 24. Now we can recognize that 24 is not a perfect square. What we do know is 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. We can see here 24 falls between these two perfect squares. It's not a perfect square itself, but what we can say is if we check down this list, 24 has a factor of 4 that is a perfect square. Now it also has 1, but what we're going to be doing is we're going to be dividing out perfect square factors, so it doesn't make sense to divide out 1. So even though 1 is a perfect square factor that is less, 1 is a perfect square factor of everything, and it won't change the way we simplify anything here. Since we've identified 4 as the only perfect square factor, again, other than 1 of 24, we'll take 24 and we will write it as a product of its perfect square factor 4 and 6. Now it is actually important that you put the perfect square factor first here, just because it makes it easier to simplify as you move forward. Now we have what's called the multiplication property of radicals. This property tells us that if we have two radicals, square root of x and square root of y, we can combine them to be square root of x times y. Since this is a statement of equality, this is also true. So, since we have 4 times 6 here, a product, that means we can split this into the square root of 4 times the square root of 6. Now this is helpful because the square root of 4 is 2, the square root of 6 is irrational, and it doesn't contain any factors that are perfect squares. So, this radical is now in simplest form. Since square root of 24 is an irrational number, 24 is not a perfect square, there's no way we can write that radical without rounding it. But we can simplify a perfect square factor out of it and write it as 2 times the square root of 6. If we look at another square root, let's take a look at the square root of x to the 7th. And let's consider what makes a variable expression a perfect square. If we think of different variable expressions here, x times x would give us x squared. X squared times x squared would give us x to the 4th. Since we're adding the exponents, x to the 3rd times x to the 3rd gives us x to the 6th. X to the 4th times x to the 4th gives us x to the 8th, and so on. What we can see here is these exponents are all divisible by 2. Remember that this isn't written here, but the index of this is 2. If you recall, x to the 7th can be written, the square root of x to the 7th can be written as x to the 7th to the 1/2. We can recall our property of exponents here is that these can be multiplied, which makes this x to the 7 over 2. So we can see here that what makes a variable a perfect square would be it having an exponent that's divisible by 2. Or to be more general, a variable expression would be a perfect nth root as long as its exponent is divisible by the index n. So we can see that x to the 7th is not a perfect square. So we're going to do something similar and look for a perfect square factor of x to the 7th. All this means is we need to find the next number under 7 that is divisible by the index of 2. In this case, that would be x to the 6th. We're trying to write x to the 7th as a product of a perfect square factor and then whatever's remaining. X to the 6th times x is x to the 7th. Now we can do exactly what we did before and break this down into the square root of x to the 6th and the square root of x. The square root of x to the 6th is x to the 3rd, and the square root of x remains the square root of x. Let's look at a cube root. Suppose we're looking to simplify the cube root of 54. Cube roots may not be as familiar, but take some numbers. Again, we can skip 1 because we're not going to divide out 1 and see any difference. But 2 to the third gives us 8. 3 to the third is 27. 4 to the third is 64. So again, we can see 54 is not a perfect square as we've passed this number and it wasn't on the list. So what we're looking to do is see if 54 has any factors that are perfect cubes and break it down into a product. We can see here that 27 is a factor of 54. So we can break this down into the cube root of 27 times 2. And again, this works the same way. The cube root of 27 times the cube root of 2. So we get the cube root of 27, which we figured out here is 3, times the cube root of 2. Again, we know this is simplified because the cube root of 2 can't be broken down anymore. 2 does not contain any factors, again, other than 1, that are perfect squares, perfect cubes. Let's look at the cube root of a variable expression. Something like the cube root of x to the 14th power. So again, we need to determine if x to the 14th is a perfect cube. So just like we said before, we're looking to see really if this exponent is divisible by the index, and you can see that it isn't. We know that x squared times x squared times x squared, or x squared cubed, is x to the 6th. And x times x times x is x to the 3rd. Sorry about that. X to the 3rd times x to the 3rd times x to the 3rd is x to the 9th. X to the 4th times x to the 4th times x to the 4th, or x to the 4th cubed, is x to the 12th. X to the 5th cubed is x to the 15th, and so on. Again, we can see x to the 14th in between these. Now, we've already determined that x to the 4th isn't a perfect cube. And with the variable expressions, the nice thing is we know that it's not a perfect cube because it's not divisible by 3, and all we're looking for is the next number other than 14, under 14, that is divisible by 3. So this doesn't really require us writing this out every time. We just need to think of the next number below 14 that's divisible by 3. We can see from writing it out that it is 12. So we have x to the 12th times x squared. Again, we use our multiplication property and split this into the cube root of x to the 12th times the cube root of x squared. Now again, the cube root of x to the 12th, we can see what we wrote here is x to the 4th because x to the 4th to the 3rd was 12, but all this actually comes down to is dividing 12 by the index of 3 to give us our new exponent. So we have x to the 4th times the cube root of x squared, and now this is simplified. And we can do this for any other higher powers of any other higher indices other than 2 and 3. So the same thing would apply to something like the 4th root of x to, say, the 18th power. So without writing this all out, we know that 18 is not divisible evenly by 4. So we're going to think of the next number under 18 that is divisible by 4, which would be 16. So we have x to the 16th times x squared, because x to the 16th times x squared is x to the 18th. And now this allows us to break this into two radicals. And again, we don't need to actually write anything out here. Since we know that 16 divided by 4 is 4, then this exponent is now x to the 4th times the 4th root of x squared. Now, if we combine these two numbers and variables, we need to just figure out a way to organize this so that we don't get confused. So let's suppose we have something like square root of 80x to the 5th. Now we can see that neither 80 or x to the 5th is a perfect square. Again, if we list out some perfect squares here, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, and then 9 squared is enough for us to see that 80, again, clearly isn't a perfect square. This isn't necessary to do every time, but it may be helpful in finding the largest perfect square factor. So what we actually want to do here is we want to break this into two pieces. Here, we'll put all the perfect square factors. And here we'll put all the non-perfect square factors. So, since we're going to take 80 and split that up, we can look down this list and actually figure out that 16 is the greatest factor of 80 that's a perfect square. 4 is also a factor of 80 that's a perfect square, but if you break this down, we can see here that 20 still has a factor of 4 that's a perfect square. This means that 4 isn't the greatest factor of 80 that is a perfect square. In this case, it's 16. So I'm going to put 16 here, and then I'm going to put 5 over here. I'm going to write this all as a product. It's just helpful if I have all the perfect squares together and all the non-perfect squares together. X to the 5th is not a perfect square. Remember that we're looking for the exponent to be divisible by the invisible 2 here. Since 5 is not divisible by 2, x to the 5th is not a perfect square. So we need the next number under 5 that is a perfect square. In this case, that's 4. So we're going to put x to the 4th here, and then we're going to leave the remaining factor of x with the non-perfect squares. This allows us to nicely break this into two radicals where the first one contains only perfect squares, and the second one contains non-perfect squares that also don't have any factors that are perfect squares. So the square root of 16x to the 4th, we can do separately. The square root of 16 is 4. The square root of x to the 4th is x squared. Remember that it's x squared because 4 divided by 2 is 2, not because the square root of 4 is 2. And then what's remaining here is the square root of 5x. And since we already know that they don't have any more perfect square factors, this is the answer. Let's look at the cube root of 24 x to the 8th, y to the 6th. So we have two variables here. Now, when we look at each of these, again, cube root, we know 2 cubed is 8, 3 cubed is 27. So we can see 24 is definitely not a perfect square, but it does contain 8 that is a factor of it. So again, we're going to break this down, and first we're going to put the perfect squares, and then we're going to put the non-perfect squares. Perfect cubes and the non-perfect cubes. So we know that 24 is not a perfect cube, but we know that its factor 8 is. So we'll put the 8 here, and then since 8 times 3 is 24, we'll put the 3 on the other side. Now x to the 8th is not a perfect cube, so because again, 8 divided by 3 doesn't go in evenly. So we're looking for the next number below 8 that is divisible by 3, which would make the exponent a perfect cube. In this case, that would be x to the 6th. X to the 6th times x squared is x to the 8th, but we'll leave the x squared, the non-perfect cube factor, on the right side. Now, y to the 6th is a perfect cube. 6 divided by 3 is 2, so we can see that y to the 6th is a perfect cube, so we don't want to break that down. If we break it down, this will actually make this more complicated. Since this is already a perfect cube, we're just going to put this with the perfect cubes, and we're not going to have a factor of y in with the non-perfect cubes. So when we simplify this, we break this into two radicals, the cube root of 8x to the 6th, y to the 6th. This is the radical we'll evaluate because they're all perfect cubes, times the cube root of 3x squared. This is the radical we'll leave by itself since none of the factors are perfect cubes. So the cube root of 8 is 2. The cube root of x to the 6th is x squared. Again, at that point, you're just dividing the exponent by the index. The cube root of y to the 6th is y squared. And then we just have what's remaining in this radical. And this is now simplified. Let's try the 5th root of 64 x to the 23rd power times y to the 6th power. So fifth roots, 2 to the 5th power is 32. 3 to the 5th power is going to be a lot larger. These get big very quickly. So it's clear that 64 is definitely not a perfect cube. But we can see that it does have a factor that is a perfect cube. So when we break this down, 32 is a perfect cube factor. Remember, the perfect cubes will go first. What's remaining on the side that's not a perfect cube is 2, since 32 times 2 is 64. Now, x to the 23rd is not a perfect fifth root. Excuse me, I said perfect cube. X to the 23rd is not a perfect fifth root because 23 is not divisible by 5. So we need to find the next number below 20 that is divisible by 5. Below 23 that is divisible by 5, which would be x to the 20th. So x to the 20th times x to the 3rd is x to the 23rd. So we'll break it down again into the perfect fifth factor plus, on the other side, the non-perfect fifth. 20 plus 3 is 23, so that gives us the x to the 23rd. In this case, y to the 6th is also not a perfect fifth. So we need to look for the next number under 6 that is divisible by the index of 5, and that would be 5. So this is y to the 5th with a remaining factor here of y. So again, we'll split this into the fifth root of 32 x to the 20th, y to the 5th, times the fifth root 2x to the 3rd times y. So we already know that the fifth root of 32 is 2. The fifth root of x to the 20th is now x to the 4th, and again, that's because 20 divided by 5 is 4, so we know the fifth root right away. The fifth root of y to the 5th is just y, because 5 divided by 5 is 1. And then what's remaining is fifth root of 2x to the 3rd times y. So this gives us a nice organized way of splitting these up to make sure that we have our perfect squares first, and then what's completely simplified under the radical, the non-perfect cubes, the non-perfect nth roots.